Okay, so today we're going to do heteroskedasticity testing for our beta calculation that we did last time. Yeah, so to start, we're going to import all the packages that we need. It should be everything. In this video, I switched up our regression. Instead of using scikit-learn, we're going to use the stats models API. It gives us a lot more detail than the scikit-learn one, and it's just kind of more intuitive overall. It kind of makes everything a lot easier than the scikit-learn one for getting variables and doing heteroskedasticity testing. So we're going to import our stock and our index. The stock I'm using is Tetra Tech. It's an engineering services firm. I just used this because it kind of fit what I was looking for when it comes to statistics and finding heteroskedasticity so we can correct for it. So to start, we get our index data and our stock data using the same get price data that we had last time. And then I'm just going to manually get the data instead of doing the calculate beta, because it really only gives us the OLS and the beta. So after this, let me just run this real quick. So now we're just gonna run our regression. This one has a little different API. You just specify the OLS and then fit it, and then you can get the summary. So you can see the summary is a lot different. I'll kind of go through this a little bit. So our R squared, I'm sure you're aware of it. It's how much variance the dependent variable in the dependent variable is explained by the independent variable. And then the adjusted R squared just adjusts for the complexity of the model. That's less important in like a simple regression like this compared to like a multiple regression. Next, we could see that our F statistic is high enough for our probability to conclude that it's different than 0, so meaning our model has an impact, or the relationship has an impact where the market influences the stock's returns. The log likelihood, this just means that it's just a goodness of fit kind of measure, with higher indicating better if we were to compare it. The AIC and BIC, they're just measures used for model selection, another comparison measure where the lower is better. It's not really super relevant here, but if we were to compare models, then it would become kind of relevant. Next, the omnibus. So this is just a measure of the skew and kurtosis, and it kind of just looks at the residuals and their distribution. So if this were less than 0.05, we might want to check into the skew and the kurtosis to see how it makes an impact on the residual distribution. Actually, let me just plot that because I have it. So we're going to create two plots initially, one for our regression right here. As you can see, it's a positive beta, and our beta is around 1.2. And then we can plot our residuals and their distribution using a plot called the QQ plot right here. So this 45-degree line is a normal distribution, and our points are the residuals on that normal distribution. As you can see, it's pretty relatively close to a normal distribution, and we can see that in the skew and the kurtosis. So we want a kurtosis of around 3 and then a skew of 0 ideally, but these are close enough where it doesn't really show an error or show a problem when it comes to the JB and the omnibus. Oh, the JB is just another goodness of fit test. In the Durbin-Watson, this isn't really super important right now. This just measures the presence of autocorrelation, and you want it around 2. And then anywhere between 2 and 4 is positive autocorrelation, and then 0 to 2 is negative autocorrelation. Moving on to the conditional. So we can see right here, this assesses multicollinearity, and above 30 has a little multicollinearity, but that's not really super relevant to what we're doing. But yeah, so this is our confidence interval for our beta, and this is what's going to be affected by the heteroskedasticity, because heteroskedasticity gives us unreliable standard errors, and that's what we're correcting for using robust standard errors down below. To test for heteroskedasticity, we're going to use the Brausch-Pagan test. So what this does is it tests the distribution of the error terms and then gives us an f-statistic and a p-value. So we can see here that our p-value is below 0.05, indicating that the null hypothesis of homoskedasticity is false, or we should reject the null and accept the alternate hypothesis of heteroskedasticity. And so now to correct for it, we're just going to refit our regression using covariance type HC1. So this is just heteroskedasticity corrected robust standard errors. So we can run this, and then we'll just run our original regression without correcting, so you can see the difference. Our standard errors for our variable, or for our beta, are between 0.998 and 1.458 on our non-robust standard errors. But if we go up, we can see that our standard error has decreased, and we get a better estimate of the variance. So this can be important because it kind of shows that there is an impact to checking for this and making sure that there is no heteroskedasticity present, and if there is, we correct for it. Because if you were to do a sensitivity analysis using beta between the confidence intervals, this would give you a completely different answer than this over a long period of time and over large investments. So this is how you correct for heteroskedasticity in your testing, and yeah, how to better read a regression result when it comes to beta. So yeah, thank you for watching. Let me know if you have any more questions, and I will be posting a CAPM video soon, so stay tuned for that. And thank you. Let me know if you have any questions or any comments. Please feel free to let me know. Thank you.